So this talks on proof of replication and its application to decentralized file storage networks. So decentralized file storage is about taking the massive amount of data currently stored in centralized data centers and spreading it over the global decentralized network of interconnected devices. And the concept is that, well, one model is that you can take all the data and store it in these centralized, massive cloud data centers, but the internet is also massively scaled, and there's billions of interconnected devices, as well as unused storage. And can we leverage those resources in order to store information distributed all across the web? One of the poster boy success stories of peer-to-peer file systems is peer-to-peer file downloads, like BitTorrent, which took the concept of if you have a whole bunch of users who are all interested in downloading the same file from a server, can they, instead of each separately downloading this file from the server, combine, share their bandwidth resources to each download a piece of the file and then exchange those tit for tat with each other? Decentralized file storage is a similar concept in that if you have a file, you'll be breaking it up into pieces perhaps, and distributing it all over the web. But now you'll have nodes which are not necessarily storing pieces of data that they are interested in downloading. They're storing any pieces of data. So you're also going to have some kind of incentive framework for incentivizing nodes in the network to actually store pieces of information that they're not interested in storing themselves. So there's already a company working on just this. It's called Pied Piper. If you saw the last season of the show. So we could talk about many different types of advantages of decentralized storage. We could talk about censorship resistance, persistent availability, self-monitoring, organic growth and optimization, monopoly disruption. But what I'm going to focus on today are two concepts. One is storage cost, and the other is storage trust. So as I already mentioned, the first question is, how are we going to incentivize data storage? What's going to incentivize these nodes to store pieces of files? And the other question for an individual who stores files in this network is, well, is my data still being stored? What do I have to do to ensure that my data is still there and available? And ideally, we would want the system to secure itself in some sense, so that you as a user don't have to continuously check that the network is still storing your files, that if you put your data in the network and went to bed and got up the next morning, that they would still be there. So the first thing we're going to look at is some kind of proof of storage and how to use it in such an environment. There are a variety of flavors of cryptographic proofs of storage that have popped up throughout the literature. One kind is proof of data possession, roughly saying, I possess this data. And a proof of retrievability is a similar concept, but it's saying that not only do I know this data, but I can efficiently extract it from my own storage. In some sense, the proof itself is a proof of extraction. There's also proofs of space. When I prove to you that I can retrieve a file, I'm not necessarily telling you anything about the resources that I'm dedicating to storing that file. In fact, if two different nodes give you a proof of retrievability of the same file, then only one of them is necessarily storing the file. A proof of space is not really related to retrieving a particular file, but it's proving that I'm using storage for something. And there's also a related concept of proof of space-time, which is that I'm using storage resources throughout a period of time. So what kind of proof of storage would we need for the network that I proposed? So if you think about if we just had the network have users directly pay for storage, then all we would really need is a proof of retrievability, right? I get a proof of retrievability from another node in the network that it stores my files, and then I would pay it in some kind of currency, say Bitcoin. But the question here is, can we somehow subsidize the cost of storage and also avoid the need to check on your own that another node is actually able to retrieve your file? So that if you weren't interested in retrieving your file for about a month, that other nodes in the network would be able to verify that it's still being stored. So there's two types of, the first question was about subsidizing storage costs. There's two types of peer-to-peer file storage costs. One, there's a transactional cost. There's a peer-to-peer payment and agreement between a user and a storage node who's agreeing to store the file. And there are going to inevitably be infrastructure costs to maintaining some kind of transactional system, whether that's a blockchain or there's middlemen involved who are processing the payment network. And now there's also this physical storage cost of actually storing a file. And so let me first give a very high-level overview of blockchain-based transactions, because the first type of cost is a transactional-based cost. So in a blockchain-based transaction system, you have this distributed append-only ledger for peer-to-peer transactions, and it's essentially a ledger with rules. It implements a state machine that takes in messages and updates its state. Could be something like A transfers a coin to B. It's a dynamic database that everybody's appending transactions to. And the main problem in maintaining such a distributed ledger of information is how do you maintain consensus on the state of this machine, the state of this payment system. You can have honest reasons why consensus would not be achieved, such as different messages being propagated at different times to different nodes in the network, and the network gets different views of the transactional order, which are incompatible with each other. You can also have malicious forks. So the way this is resolved is by designing some kind of simple consensus rule, like we'll maintain all the transactions in a chain, and you'll also just choose the longest chain of transactions, consistent transaction that you have heard so far. The problem was that this was not enough. It's cheap to add transaction blocks. It's called a Sybil attack. So one solution is this proof of work-based solution to add cost to building a chain of transactions. And Bitcoin's proof of work grew over the years to incurring a huge amount of work. Right? As miners were incentivized to join this network, the hash rate increased exponentially. And in fact, people have done studies to show that in this kind of model of a transactional network, the reward itself is somehow necessary for the stability of the consensus protocol. Now, of course, there's other kinds of proofs of resource similar to proof of work that have been proposed, such as proof of disk space utilization or proof of ownership of value. So how is this related? Let's come back to our goal, which was to deal with the cost, both the cost of transacting in a system, asking another node in the network and paying that node to store your data, and also the actual cost of storing data itself. And so we wanted to subsidize the cost of storage. So the idea here is to use a blockchain-based transaction system for the payment. And instead of just using any kind of proof of work, we use the proof of storage itself as the proof of work that powers the transactional system. So it's this double utilization of a resource that should cover the cost of both interactions. One, storing the actual data, and two, having a transactional system to agree for another node to store your data and also pay that node to store your data a minimal amount. So the idea is that the cost of storage is subsidized through these mining rewards for proof of storage as this blockchain-based proof of work. Now, it's very tricky to design a proof of storage that would be able to support these properties. For instance, if we just used a proof of retrievability, then a server could generate just a large amount of junk data on the fly from a small seed and claim that as their proof of work, but it really didn't require any utilization of resources to do so. In fact, it's really necessary for the proof of space and the proof of retrievability to share the same storage resources as well. Why? Let's say that you separately gave a proof of space and a proof of retrievability that you could retrieve some file. Then you would need to use two separate disks for each of these tasks, one to actually store the file that you're proving you can retrieve, and the other, which you're using for this proof of space, which may not use the same resources. And so now it's actually less costly to prove retrievability of some junk data generated from a seed, because then you don't have to store that. And in fact, it increases the cost for storing actual users' files, because now we have to cover your opportunity cost for using that second disk just to give a proof of space and get rewards from the blockchain. So what we want is a proof that you're dedicating unique resources to storing some replica of the data that you're claiming to store, or that a user requests for you to store, even if you can generate all that data from a small seed. There's an additional benefit from this, which is that you could ask two different servers to store a copy of the same file, perhaps because you want better availability or better fault tolerance. And while you can't really guarantee that these two servers are individually storing the file, they're not just having one server store both copies of the file on their physical machine without some location-based proof, you at least remove the incentive for the two servers to deduplicate the storage and share the same resources. So another way of thinking about this proof of replication is that you're proving that you're dedicating unique resources to storing and replicas of the same file, even if you know the file's contents. And that's where we get this term, proof of replication. So one of the goals of this project was to come up with a cryptographic way of thinking about proof of replication as well. It turns out that formally modeling is also tricky, and it informs the type of security that you're really trying to prove when you construct such a system. So proof of replication involves some setup protocol which generates a replica of the file that you're going to replicate. It has a prove algorithm where a server takes this replica and takes in some challenge and is able to generate some kind of proof. And then there's a verify algorithm that would take in the proof and some information about the original file, whether it's the file itself or some commitment to that file, and either reject or accept the proof. The way that these algorithms are used in the interactive proof of replication protocol is that there will be this setup phase, which will take perhaps a long period of time. And then there will be this online phase where the verifier will challenge the prover to produce a proof within a short period of time. And if the prover fails to produce the proof within that period of time, then the verifier will just automatically reject the proof. The reason why you have this time axis is essentially to capture inherent time-space trade-offs that you have in proofs of space or proofs of storage, where you can always spend more time to prove that and use less space to pass a proof of space, but by limiting the time that the adversary or the adversarial prover has to run, you can achieve this unconditionally secure property that the prover will not be able to pass the proof without actually using enough space to pass the proof. So again, towards this cryptographic definition, we have this setup phase and this challenge phase, and we can model the security in terms of a game between an adversary who's deviating from the honest prover strategy and a challenger who's going to challenge this adversary to produce proofs. The first thing we want is retrievability, just like a proof of retrievability, that if the adversary passes the proof, then there exists some kind of extraction algorithm that can look at the adversary's state and extract the original data. We also want to have a space property, which says that if we look at the adversary's space utilization during any snapshot during the challenge phase, that the adversary must be using at least some 1 minus epsilon times n space, where n could be at least the size of the file. We might want to make it a little bit larger even. And we also don't want we want this space property to capture this non-amortization property, that if the adversary produces 2 different replications of the same file or different files, that it must be using 2 times the space. Right? Now, finally, there's this replication property, which is really the trickiest part to capture. And it's what's missed between just a proof of retrievability and a proof of space. And you can think back to that example where if you just separately produce a proof of retrievability and a proof of space, then there's nothing that forces you to utilize the same resources to do both of these. And so our first attempt would be to just capture our intuition about what retrievability is, what proof of replication is, and say that, oh, if we looked at the adversary's state during any period of time during the challenge, that we'd be able to divide its state into 2 separate parts, from each of which we could extract a copy of the file. That would capture our intuition that, okay, this adversary must be storing 2 distinct replicas of the file and dedicating resources to do so. The problem with this seemingly great intuition for a security property is that it's impossible to achieve that. It would be easy for the adversary to just change its strategy slightly. Say that we take a good adversary, which is able to divide its storage into 2 parts, which each store a replica of the file. Then it could do some trivial thing like encrypting the first replica with a hash of the second replica to correlate its data. And now you can't partition this state into 2 parts that each independently encode the data. Yet the adversary would still be able to run the successful strategy by easily decoding this and passing the proof. So we don't really mind an adversary that does that, but it, again, wouldn't pass that too strong of a security definition. So what we really want is this concept of a rational adversary, where the rational adversary may do something that deviates from the honest protocol, but they don't really save anything by doing that. So this rational adversary has been used many times before, especially within the realm of similar protocols like proofs of space. And the concept is that for any adversary strategy, there should be just an efficient way to switch between a good strategy and a bad strategy. Now, that actually doesn't capture everything just quite yet. There's also this other thing that we need to show, which is that you can't embed other useful data inside a proof of replication. Why? Because let's say that you were using these space resources to pass both your proof of retrievability and your proof of space, but you also have some external copy of the file that you could use to pass the proof of retrievability as well. We want to show that in such a scenario, you wouldn't be able to use the space resources that you're using for this proof to embed other useful data by deviating from the honest strategy. So we want to show somehow that any adversary that can pass this proof must be using these unique resources to passing the proof that also can't embed other useful data. And it's hard to show that again for very similar reasons to the previous one. Roughly because, again, you can't guarantee that the specific bits of the replica are being stored. There would be some way to encrypt it and store the key elsewhere. But roughly speaking, the way that we prove this same rational adversary definition of security is by showing the incompressibility of this replica and showing that intuitively this adversary still cannot use this space to encode any other useful data. So now on to the performance considerations for such a system. We want it to be scalable. We want it to maintain security and performance for arbitrarily large files. We want there to be low communication. We don't want the prover to have to send back the entire file as a proof. So we want compact proofs that are smaller than the file size, as well as trying to reduce as much as possible the frequency of polling between the verifier and the prover. And finally, fast verification. We want the complexity of the verifier to be small compared to the prover. So I'll first explain a basic proof of replication. And the main tool for this proof is a verifiable time delay encoding. You can think of this informally as an encoding of a file that takes a slow amount of time to encode in terms of wall clock time, even with parallelized effort. But on the other hand, it's fast to decode. So a bad example of this would be to iterate an encryption many times. That's a slow encoding, but it's not fast to decode. There are better examples of this that have been proposed over the years, several which I have cited here, but this talk is not about those encodings. We're going to use this encoding as a black box to create a basic proof of replication. So how is this going to work? So the prover is going to use this time delay encoding in order to encode the file during the setup phase. And then during the challenge phase, the verifier, here's a straw man proposal, would request the file and then decode it to check that it matches the original file. And the concept here is that the server cannot respond quickly enough if it deletes an encoded replica, the encoded replica of the file. The problem with this straw man proposal is that it's not communication efficient, right? Because sending over a replica of the file is just as costly as sending over the entire file, okay? So while this might work for small files, it at least has the property that because this prover is required to generate a unique encoding that takes a long time to derive, just by being able to query another server who's storing a copy of the file, it wouldn't be able to pass this proof quickly in the challenge phase. Because if it deletes the encoding of the slow encoding of the file, it won't be able to rederive it in the time. But again, it's not communication efficient. So what would we do about larger files? Well, one idea would be to encode each block of the file separately. We break the file up into blocks, and then we do a slow encoding of each block separately. And then what we could do is the verifier would query just for a randomly sampled constant number of blocks in order to gain confidence that, say, 90% of the blocks are being stored. And if we also apply erasure codes to the original data, then that would amplify this confidence to 100%. Great, but because each encoding is very expensive, then this scales horribly as the file grows to be very large, right? Now the total amount of work that the server has to do to encode, say, 1 billion blocks would be 1 billion times the amount of time it would have to spend to encode one block. And because this time delay encoding is independently tuned to just the amount of time it takes to encode any block, this would basically be an infeasible protocol. Moreover, it's highly parallelizable for the adversary, so We can't assume that we allow more time for an honest prover to be able to generate each of these encodings separately, but then an adversary who uses a lot of parallelism can derive them much more quickly. So the concept we're going to explore is to add chained dependencies between the encodings of each of these separate blocks. So let me propose another straw man idea. What if we used some kind of cipher block chaining encoding, similar to CBC encryption? So what we would do is we would apply the encoding to the first block to derive that encoding. Then we would XOR that with the second plain text block and derive the encoding of that one, and so on and so forth until we derive some kind of encoding of the entire set of blocks. And now what we could do is adjust because this is a sequential process, we could adjust the delay cost of each encoding so that the total time to encode all the blocks remains the same. Now the verifier can still query for some constant number of blocks and decode it efficiently. So let's say they asked for the third block here, then they could ask for just the third block and its predecessor. And given the third block and its predecessor, they could quickly decode it to check that it matches the third plain text block. The problem is that this very property also gives rise to an attack. What if the adversary only stores every other block, reducing its storage by half, and in a way that it's not actually able to retrieve a copy of the file unless it had some external access to the file, say like one being stored by another server? Then if it only stored half of every other block, when challenged for, say, the second block, it could quickly derive the encoding from the plain text and from the first encoding that it's storing. Similarly for the fourth block. So by decreasing the amount of time that the encoding is going to take proportional to the number of blocks that were being stored, we introduced an attack. So the idea is to improve on this naive way of chaining the dependencies between the encodings of these blocks and to use a much smarter way of chaining them. Not to chain them just linearly in a sequential cipher block chaining mode, but to use what I'm calling a depth-robust chaining. And the reason I'm calling them a depth-robust chaining is because it's derived from these graph structures that have this depth robustness property, which I'll explain in a moment. But the idea is to derive the dependencies according to the edges of a more complex graph. That's not just a linear chain. And we still want to maintain verifier efficiency so that the number of predecessors of any given block is still small so that the verifier can query for just some number of these encodings and their predecessors and decode efficiently to check correctness. So there's two types of directed acyclic graphs that we can use. One are depth-robust graphs, and the property of depth-robust graphs that's useful to us is that any large set of removed nodes contains a long dependency path in it. Okay, so that if the adversary deletes some large fraction of the nodes, then there will be a long dependency path within that large fraction of nodes deleted, and so they'll have to rederive all the nodes within that deleted portion of the graph with high probability, and in order to do so, they'll have to do a lot of sequential work. The other types of graphs we can use are just more generally hard-to-pebble graphs. But if we were to go away from depth-robust graphs to just hard-to-pebble graphs, then we wouldn't necessarily maintain this sequential guarantee. There would be a perhaps large time-space trade-off for the adversary, but we wouldn't be able to maintain this unconditional property that within the allocated period of time, the server would not be able to pass the proof if they had deleted too many of the blocks. So again, just to summarize, the depth robust graphs have this property that if you delete a subgraph with sufficiently large, comprises a sufficiently large fraction of the nodes, then it contains a long path. And in fact, we can show that many nodes in the subgraph have high depth. So plugging this back into the protocol, the prover will derive a encoding of the file in the way described using these chain dependencies among blocks according to the edges of a depth robust graph. And then the verifier will request labels on just a few of the nodes and check for correctness. So in summary, we've designed this proof of replication secure under this proposed rational adversarial model for proof of replication. We have a feasible and scalable setup, which can remain, well, roughly constant as the file size grows until a certain point, of course. And then low communication, there's compact proofs, as well as fast and low complexity verification. OK, thank you very much.
Say this is actually being used. This will be or being used by.
Yeah, Filecoin was one of is a recent blockchain-based cryptocurrency project that is using proof of replication like this in order to back IPFS, which is a decentralized file storage network. So they're using this. They're going to use this protocol in order to back that network. So, yeah.
Any questions? This is, by the way, oh yeah, there's a question in the back, yes.
What is the basis for the assumption that there will be no economically efficient concentration of storage if there is money in this? In the past, we had this with CPU when we had thousands of miners, and today we have 4. So why will not a storage economy evolve so that a couple entities can buy thousands of petabytes of storage and own the network?
Yeah, there's no such assumption. In fact, that's a very valid thing to consider as an alternative to this model. This model does not capture that, but that's something that you would have to see in terms of how it would play out. Yeah.
2 questions.
Yeah.
One is, are there any real-time usage of this protocol now? And second is, was slicing considered in term with replication, as in like slicing versus replication?
Slicing in terms of David Mazieres' protocol?
Yeah, Standler.
Yeah, no, so the protocol, the Federated Byzantine Agreement Protocol that David was explaining is in a completely different model of consensus. So there wasn't any consideration of combining them. I mean, maybe there's some interesting concept, but here the very concept is using the proof of storage as a form of mining proof of work. So it's a completely different model. But are there any real-time? You said, is there any real-time use of this yet? No, this is entirely under development, but hopefully soon there will be.
So you'll be able to store your data pretty soon.
Perhaps.
Right?
Yeah.
Terrific. Okay, so thanks, Ben.
Thank you.
Cool.